Hey, welcome everyone to the Astrobit podcast, brought to you via your home for curated space news, astrobitica.com. I'm your host, Alan, the Astro Writer, and this is the next episode of Astro Wife Asks. In this segment, my lovely wife, Raylene, the Astro Wife,
hi everybody,
asks me about an astrophysical, astronomical, or space-related subject she's curious about, and I do my best to explain it. It's a fun way to dive into the wonders of the cosmos while keeping things approachable and conversational. So without further ado, Astro Wife, what do you want to ask about today?
So today I would like to learn about what Lagrange points are and why they are important in space.
Yay! Okay, so Lagrange points. This is, I'm excited. This is a topic that I'm very interested in. It's so much so, it's what I wrote my master's thesis on. And I've studied them for years, so I'm glad we're talking about this one today.
I figured it was time we spoke about this one because you're very passionate about them.
Yeah, I just got to be careful or this will be a 45-minute podcast. Okay. The fun way to think about Lagrange points is that they are these little pockets of gravitational stability that exist everywhere in the universe, but mostly around two bodies that are in orbit of each other. So think of like the Earth and the Moon. They have Lagrange points. The Sun and the Earth, they have Lagrange points. And they work because they are these points where there's the balance of these two forces. Okay, so the first force is the centrifugal force. You ever heard of that one?
Mm-hmm.
All right, so
objects spin around each other?
Yeah, so when you're going around a merry-go-round, and you feel like you're going to fly off the merry-go-round if it were to go faster and faster, that's centrifugal force. All right, think of it like spin force. The other force is gravity, right? And we're all familiar with gravity. So think of it like centrifugal force wants to push you away, and gravity wants to pull you in. So there are these certain points where there's a balance where the push and pull between kind of even out, and you become gravitationally stable. And think of it like, so the first one, well, we have to cover a little bit of Kepler's laws of planetary motion. We're not going to go super deep into it. But one of Kepler's laws is the closer you are to a body, like the sun, right, the faster you move, right? So Mercury, as we've discussed before, like physically moves faster through space because it is closer to the sun than Earth does. Earth is further away, so it moves slower. All right.
And Pluto moves super slow.
And Pluto moves crazy slow because he's
Pluto.
way out there. All right. All right. So if you were on Earth and you were to look inward to the sun, everything should be moving faster than you are, right?
Okay.
But if you put a small body, so like a satellite or even like a really small asteroid, if you put it at a certain distance between the Earth and the sun, the gravity from Earth starts to pull against the gravity of the sun to where it balances. So where an object should be moving faster, it will actually move at the same speed as the Earth, even though the Earth is further away. And then the same thing is true on the opposite side. So if you go way out away from Earth, away from the sun, there's this balance point to where like the centrifugal force of the sun wants to shoot that body off, right? Because it's traveling. And there's the combined gravitational pull between the sun and the Earth is pulling that body closer, making it stable. So there are 5 Lagrange points. I've already given you 2. The first one is like on the inside of the two bodies. The second one is on the outside of the smaller body. The third one is at the same point 180 degrees of where the smaller body is. So you think like the Earth is orbiting the sun. If you go 180 degrees ahead of or behind that orbit, right, along that same orbital path, that's Lagrange point 3. So if you're looking at it like top down, Lagrange point 3, 1, and 2 are in a straight line from each other, right? From like the opposite side of the sun, go through the sun, then there's the first one, then go through the Earth, and then there's the second one on the far side. Those are called the linear or collinear points. Lagrange points 4 and 5 are along the orbital path of Earth, but they are 60 degrees behind for 4 and 60 degrees ahead of for 5. And those are called the triangular points because if you take that Lagrange point plus the main body, which is like the sun, plus the smaller body, which is Earth, it forms an equilateral triangle. So those are the 5 Lagrange points. Now, the collinear points, the 3 points, are less stable than 4 or 5. So the way I've always heard it and had it explained is if you were to take a marble and you were to take a bowl, like a cereal bowl, and you turn the bowl upside down and you put a marble on top of that bowl, the marble will be relatively stable. But if you shake that bowl enough, the marble will fly off. That is Lagrange point 1, 2, and 3. But if you turn that bowl upside down, like the right way, and you put the marble inside the bowl, it takes a lot to shake that marble out of the bowl. So it's very stable. So those are L4 and L5. Right.
So would most satellites then get positioned at L4 and L5 then because of the stability?
All right. So it depends on the application. What is your goal, or what do you aim to achieve with the satellite? And this is what I did my research in, Lagrange point applications. Okay. So we use them, different Lagrange points for different things. So the very first Lagrange point we ever used was the Sun-Earth L1. It's that one on the inside of Earth's orbital path. And we put a solar physics observatory there. So basically a satellite that just studied the sun. Why? Because it's in this perfect position, unobstructed by Earth, unobstructed by Earth's atmosphere, to just observe the Earth, or observe the sun full time. Right? Lagrange point 2, way outside of Earth, is where we put the James Webb Space Telescope. Right? Because James Webb is not looking at the sun; it's looking out into the deep universe, at galaxies billions of light years away. Right? And we could do a whole show just on how James Webb works. But it's out there because it's getting this unobstructed view away from Earth and its atmosphere, and it has its back to the sun, so it's not being obscured by the sun's light or anything like that. So it depends on what you want to use, or what is your goal for your satellite, depending on where you put them. There have been proposals, and we have done satellites at the L4 and L5 point, also looking at the sun. And there's I forget what they're like, but stereophysics, where you're looking at the sun at the same time, but 2 different angles to get a more comprehensive picture of what's going on with the sun. And there's more proposals for that. But yeah, it depends on what you want, or what is the goal of your satellite, depending on which one you put it in. Because just because 1, 2, and 3 are less stable, it doesn't, detract from their
uses.
Yeah, from their uses. Like James Webb, it's way out there at Sun-Earth L2, and it's actually, not to get super technical, it's doing what's called a halo orbit around L2. So it's kind of orbiting the space itself, orbiting this empty Lagrange point itself. But it's still stable enough that we could put a satellite there. And, things that we put at Lagrange points can just stay there unperturbed, which means they won't fall out of their orbit. They won't shoot off into deep space for millions and millions of years. That's what makes them so attractive, is they are just so gravitationally stable. You don't have to use fuel or anything like that to keep its orbit stable.
So I've also heard that because L4 and L5 are like the more ideal Lagrange points, they've also been referred to as Trojan points.
Okay, so the Trojan points get their name from, so we know Jupiter is the biggest planet in the solar system.
And the best planet.
And your opinion is the best planet. And because Jupiter is so large, right, Lagrange points, the size of the points themselves are relative to the size of the bodies they exist around.
Oh,
right?
So Jupiter's Lagrange points are much larger.
Yeah, they're much bigger. They occupy more space than, say, the Moon-Earth, the Earth-Moon Lagrange points. So around Jupiter, at the L4 and L5 positions, right, ahead of Jupiter's orbit and behind Jupiter's orbit, we have these collection of asteroids that have been captured by this gravitational stability, and we called them the Trojan asteroids. Those at L4, which are ahead of Jupiter, were called the Trojan asteroids, and those at L5 behind Jupiter are called the Greek asteroids. And it goes back to, astronomers name everything after mythology as much as they can, right? So we called them the Trojan asteroids, and we've kind of taken that name and applied it to the L4 and L5 points to call them the Trojan points. But it goes to show you that it's not just you can put satellites there, right? The Lagrange points are homes to asteroids and comets and all kinds of space dust and debris that have just been traveling through the solar system.
And then they just get caught there?
Yeah, they just get captured in these little gravitational pockets, and they just stay there for millions and billions of years. We think some of the Trojan asteroids around Jupiter have been there since the formation of the solar system itself. It was just material that never got coalesced into a planet or fell into the sun at any point in time, so they've just been there. And we have NASA has a probe that's headed out there right now. It's called the Lucy probe, and Lucy is on her way to the Sun Jupiter L4 Trojan points to study some of those asteroids. And they called it Lucy because I'm not an anthropologist, right? But Lucy was like a very early hominid, a very, very early ancestor to humans that we discovered that was like really well preserved. So they named her Lucy, and I forget what Lucy stands for.
Wasn't that discovered in South Africa?
I don't remember. Like I said, not my field really. I just know she was like a very, very early human that was really well preserved. So NASA named this probe Lucy as a way to study the early ancestor of the solar system, which
That's
we think those
cool.
asteroids are out there.
Before we close out, what is seeing as you did your master's thesis on this topic, what is the coolest thing about Lagrange points that most people don't know, in your opinion?
I have this fascination with them. My favorite one is any of the L3 points, because L3 is on the opposite side of the main body, right? So you got to think where Earth is now. L3 is where Earth will be in 6 months, right? Okay. It's way out there in the empty vacuum of space.
Opposite side of the sun.
Opposite side of the sun, and the other side of its orbital path. One of my hypotheses that I questioned in my research was, is there an application or a use for L3 that we haven't discovered? Turns out no, right? Oh. But L3 has been a point, if you look in history, of fascination for a lot of people. There for a very long time, back in the early 20th century, late 19th century, people thought there was another planet there.
Really?
Yeah, they called it Vulcan. They thought that's where the planet Vulcan was. And Vulcan was supposed to be the same size as Earth and all this stuff. And you would never see it because it would always be on the opposite side of the sun from where you are. Mm-hmm. So you would never get a good look at it. But gravitationally, we thought it should exist because the Lagrange point is there.
Yeah.
And to me, L3, I don't know, there's no real use for it that you can't use L1 for or L4 or L5. But it's this little pocket of just stability out there in the quiet chaos of space, and it's just this little quiet, calm spot. I don't know. I find that really fascinating. There's no real practical application for it.
Or at least not what we found yet.
Yeah. Theoretically, there could be an asteroid there, just hanging out in that spot. We would never know unless we sent a probe out there or got to look at it from some other angle. Mm-hmm. But I like L3s because they're just like these little hidden pockets. Because Lagrange points themselves, like the universe is rather chaotic and destructive, right? Yeah. The universe is, a very hostile place. And Lagrange points are just these little pockets of calmness and stability in an otherwise chaotic and disruptive universe. And that's why I find them really interesting.
That's cool. That's very interesting.
Yeah. So those are Lagrange points. There's all types of applications for them. When we go to Mars, we're going to use Lagrange points as like docking points and layover spots to get to Mars. And when we go to the moon again, we're going to use a lot of the Earth Moon, especially like Earth Moon L1 and L2 for like refueling stations and staging stations. So Lagrange points are more important now than they probably have been in the past. There's a lot of future applications that we just now have the technology to use for them. So be looking out, especially when you're reading news, especially on Astrobitica. If you see something about Lagrange points, pay attention because they're going to be in use a lot in the coming decades, I think.
Cool. Thank you. That was very interesting.
Yeah. Well, thank you so much for tuning into this episode of the AstroBit podcast. And I hope you enjoyed our conversation and maybe learned something new along the way. If you want to explore more curated space news, don't forget to check out astrobitica.com and follow us for updates on future episodes. Until next time, keep looking up and stay curious.
Bye, everybody.